just to bring all of us to common denominator, I will start with something which you all know. Just it will help me to make next step. So I will define a definition which comes from Weyl, 1916. So I will define the notion a of uniformly distributed sequence. Sequence Xn in say 0-1 interval is UD uniformly distributed if for any subinterval it visits this interval fairly. So I hope this definition is clear. It has obviously some probabilistic feel. Suppose you have a gun. Don't go, oh, it's recorded. Suppose you have a special toy gun, which allows you to shoot randomly at 0-1 interval, and if it's totally random, or if you're totally drunk, it should get to subinterval AB with the same probability than to any other interval of the same length. And it should hit every subinterval with appropriate frequency. And that's what is postulated here. Of course, Xn doesn't have to be random to satisfy this, and we'll see examples very soon of very deterministic sequences. So that's definition which is actually equivalent to the following. For any continuous function.
Cannot be due to, Yeah, this equivalence due to Weyl. I said the definition is not due to Weyl.
Yeah, for any continuous function, 1 over m f of xn goes to integral of f dx. And that's what you had in mind? No.
Sorry, the definition is not due to Weyl, presumably.
It is.
The definition.
Weyl was the first one
to
introduce the notion of uniform distribution, and it took Weyl to introduce it. So Hardy and Littlewood were playing with some game, I will tell you in a moment, which Weyl only was able to clarify and explain, and that's why Hardy and Littlewood didn't publish a paper which they promised at one of the math congresses, because it became not interesting after what Weyl did. And by the way, as natural for us are things, especially of this kind. Here, if you first time see it, I don't think there is anyone here who sees it first time, but if you see it first time, and when they teach undergraduates, those who see it first time, not necessarily accept easily that it's possible. Because you have a single sequence, which should spend, suppose this subinterval is of length 1/10, so the sequence has to spend 1/10 of its life in this fixed interval, but also it will spend 1/10 of its life in any other interval of length 1/10. And it also applies to all possible other intervals of different lengths. And that's a little bit too much to request. Of course, we all know, for at least technical mathematical reasons, that it's possible. But ideologically, I think it's, to me at least, until now, it's not so obvious that it's possible. So for those of you to whom it is obvious, and I guess it's majority, you are lucky. So in any case, these are two equivalent statements. And indeed, if you would apply it to function and put it here, you will count exactly the number of hits. This is characteristic function of set AB, interval AB. You will count exactly this quantity, and so this is indeed now clearly similar thing. And there is actually one extra remark to make. Here I said continuous, equivalently so I could say Riemann integrable. And this function, of course, is not continuous, but it's Riemann integrable, and things are the same. Now, if you want my opinion, mathematician of the level of Weyl should be the first one to prove ergodic theory. Because it is in this statement, in this definition, you have explicitly a manifestation of what I would call ergodic principle. Namely, time average, suppose your sequence appears every second, okay, every next term. It's time average. And this is space average. Our space has measure 1, so otherwise I would divide by measure of space. So this is an example of, I repeat, ergodic principle. Time average equals space average. That's exactly what ergodic theory does. The original ergodic theorem of von Neumann was to explain, that's why the title of his paper was Quasi-Ergodic Hypothesis, because physicists thought that it's always the case. And he explained that this is the case when you have ergodic system. So I will say a few words about this very soon. And now you could ask what are examples of uniformly distributed sequences. And of course we can start with an alpha. By the way, I take sequence in 0-1 interval. If it is not in 0-1 interval, I will be reducing it modulo 1, and sometimes omitting this. But now I will write mod 1. And that's, by the way, something you can do totally elementarily by using either of these definitions. The easiest way to do it is to apply xn to functions of the form e2 pi I n x cosec k. And for each of these functions, if you substitute an alpha instead of x, it will be arithmetic progression. And you can sum up, or geometric progression, because it's in powers. And you will sum up and see that it really collapses. And such functions, by a version of Weierstrass, generate all continuous functions. Right? Trigonometric polynomials are dense in continuous functions on the torus. I don't see any reaction here. Am I talking about things which are too trivial and well known, then I will speed up. And in any case, so far we agree with everything I said?
No.
Yes, who didn't? Yes, please.
Alpha should be something.
First of all, that's true, of course, I said it not. That's not matter of agreement, that's matter of catching my typo. Thank you. The rest is okay? Well, too bad, because I cheated you in one place. You see, if I apply it only to functions which are these trigonometric functions, they are periodic, so they have the same values at the ends of the interval. And we started here with any continuous function. So I leave it to you to connect the dots and to make it still rigorous, okay? But there is a subtle thing. It's one thing, denseness of trigonometric polynomials in the space of periodic functions, and the other thing is denseness of, say, regular polynomials in the continuous functions on closed interval. For our purposes, it doesn't matter, but there is some subtlety here, which I sort of omitted, and you didn't catch me. So let's go make the next step. And next step is more interesting examples. So n square alpha. Again, alpha, of course, now I should not forget it. And indeed, any polynomial having irrational coefficients. And this is famous Weyl theorem on equidistribution of polynomials. We'll get to it from the other end, so I will not specify now. There are many, many more examples about n 3/2 times log square n. Many log-logish things, if they grow fast enough, will be good for uniform distribution. Of course, everything mod 1. Now, since one of the things explained in the abstract or in the even title is how to apply unique ergodicity, so I should go to unique ergodicity and show that some of these things follow naturally from ergodic theory. You may still want to think how Weyl proved that. So I can tell you, but maybe not now because it's not my goal, okay? How Weyl proved n square alpha. He didn't use unique ergodicity. Okay, now, before I go to unique ergodicity, I want to formulate again just to stress.
Question?
Yes, please.
Could you also show some tricky non-example, something which looks like example but is not?
Well, this you can do by hand. Take any dense subsequence in the first half of the interval. Order it any way you want. It will not be uniformly distributed.
But what about formula, like log n to power 1?
No, log to no power. This one, mod 1 of course. This one is non-uniformly distributed for stupid reason. It's just too slow. So if you would apply a little bit modified notion of uniform distribution, and that's not my goal to deal with this, so don't let me to continue. But it's an interesting topic, how methods of summation can help you take care of slower sequences. This is just stronger method of summation. It is good for that, and still equally good for those things which regular Cesaro takes. And then you could ask, well, how about log n? And then you will, so I told you not to let me go in this direction, but if you take log n, then you will have to modify this method of summation, and you will take something like log here, and then summation f of xn over log here, and again things work. So it's a very interesting thing. But that's not related to what I wanted to talk about today, and for you not to even start asking questions, I can erase it here. And there are many interesting questions. Suppose you have a decent function depending on parameter. For which parameters you have it, for which not. Already here you have some exceptions. This time it is rational numbers. There are plenty of very interesting examples of, say, this form. And so on. We know plenty about such things. These are so-called generalized polynomials. I could put here power 17 and here cube. And there is plenty of knowledge. And since I will hardly have time to explain more, such things can be well treated because of dynamics again. And this dynamics comes as dynamics of translations on nil manifolds. So if I will have a few minutes, I would add on this topic. But that's an interesting connection on its own. Translations on homogeneous spaces which are nil manifolds, these are factor spaces of Heisenberg group, say, over R by Heisenberg group over Z. That's where you start getting such things and knowledge why they are uniformly distributed. So I will erase this again here. And now I want just to stress the ergodic point. I want to formulate ergodic theorem because it's a classical thing. So let me start maybe for any x, b, mu, t, for any for any function f in L1 of x, 1 over n, f of t n x converges almost everywhere to some limit. And if t is ergodic, and this means t has no non-trivial invariant sets, then 1 over n f of t and x converges to integral of f almost everywhere. And I hope you see natural connection between this kind of statement, which is already pure ergodic theory, with this kind of statement. Here, of course, our sequence is very special. It's an orbit of a point. But the statement is totally of the same nature. Time average equals space average. And there is one subtlety. Subtlety is that this is true only and cannot be improved really. Almost everywhere. Not every point will have this property. But for totally general setup, almost every point will have this property. So for almost every x, the orbit is uniformly distributed. You have to add a little bit rigor to what I said now. I said orbit is almost uniformly distributed, but our definition of uniform distribution was in 0-1 interval. Here we have to think how do you define or what you mean by uniform distribution in abstract measure space. But suppose your abstract measure space is nice compact space, then it makes it even easier. Still, this almost everywhere rather than every remains an interesting nuisance. Okay. And that's why everyone should like the notion of unique ergodicity. So here's new definition. So let X be a compact metric space, and let T be a homeomorphism, a self. So T, yes, self homeomorphism, say. Then xt is called, so before I will write something, let me tell you that there is a classical theorem of Bogolubov-Krylov proved in mid-30s of previous century, which tells you that when you start with this setup, there is always an invariant measure on Borel sets. So you have compact metric space, you have open sets, they generate sigma algebra, it's called Borel sets. On Borel sets, it turns out you always have invariant measure. That's enormously useful in general theorem. And there are many such invariant measures. For example, if you take 2, 1, 1, 1, which maps T2 to itself, there are zillions of invariant measures. The Lebesgue measure is invariant. It's mod 1, of course. The action, should I explain the action better? It acts T2 to itself because R2 is invariant and Z2 is invariant with respect to this matrix, so it induces natural action by hyperbolic automorphism on T2. Should I explain more?
No, but maybe your formula actually defines the measure, right?
Which formula?
Averaging over an orbit, it doesn't. Can you use that to define the measure?
But I started with function in L1, so measure was already present in my assumption even about function.
Take the characteristic function of a Borel set, for example.
Or how I measure this end result here. How do I get this number if I don't have measure?
Well, because you have the left-hand side.
No, there are two things. First of all, existence of average, but I'm already here in measure preserving situation. So here I started with having measure. Here I started with not having yet any measure. I'm about to introduce invariant measure.
My point was just that the left-hand side of this limit thing, determines the measure.
Almost every is not defined.
Almost everywhere is not defined, I guess.
Without a measure.
No, maybe it's two-way street, as you say. So if I know that limit always exists and to the same constant, then maybe there is a measure, and maybe it's even unique. That's a good point. But at this stage, here I started with having invariant measure, and in many, many classical situations, it's there. But suppose I have only homeomorphism of abstract compact space. It's a pleasant news that there is always an invariant measure. So the point I was making, that this measure, which is always there by Bogolubov-Krylov, is not necessarily unique, and I started giving this example. The example is of a hyperbolic transformation of two torus. It obviously preserves Lebesgue measure, but it preserves plenty of other measures. There are, let me say it, uncountably many invariant measures for this transformation. Some of them are visible, for example, those which are sitting on periodic points. But there are others. So it's complicated, potentially, thing when you are interested in variety and qualities of invariant measures.
So is the point that only one of them can be ergodic, or?
I still didn't make my point for this transformation. The point was, I made the point that there are many invariant measures. For each of those measures, you can consider this kind of statement, because the measure here is fixed. For each measure, you can consider this kind of statement. Let me summarize what I told you so far. If you have an invariant measure, you have ergodic theorem. That's here. If you don't have invariant measure, but you want still to do something interesting, you invoke Bogoliubov-Krylov, and it will tell you that there is an invariant measure. This was only an illustration that there are many potentially invariant measures.
But I think maybe Piotr also wanted to make a point that in principle, ergodicity of the transformation can also depend on the measure you choose.
Of course.
No, but the question is, so you have many measures. Can many of them be ergodic?
Yes. Yes.
Well, for the notion of largeness which each of them defines. Some of them may be literally singular. I could give you more specific examples, but maybe for now we are happy, right? So then I will, is uniquely ergodic if there exists unique T. By the way, in my definition from the first lecture, when I talk about measure preserving system, this mu is always normalized, so it's probability measure. Here I want to postulate it, to have uniqueness. There exists unique T invariant probability measure on Borel sets of X. So, and from now on I may refer to system xt, or maybe better to system x mu t, right? Because that's what is UE of interest for me. Any questions so far? So we just
whether perhaps there are questions in Kiev.
Okay, please.
Not, yes, there are.
Could you once again elaborate on the theorem you written that we have for all functions from L1, and do we suppose that for all functions this sum converges almost everywhere, or we only choose some one function and for it suppose it?
No, I chose one for any f. This converges almost everywhere, and it's pre-assumed that it depends on f. So for another function, it will be another set of full measure when you will get convergence. By the way, I'm not sure if connection works.
And that's on their side.
But we suppose that for each function it converges almost everywhere.
Exactly.
Don't assume, no, it's the conclusion. It's the conclusion, not an assumption. He's mixing
He said not assume, he said suppose, and that's between. So,
Kiev, did you hear the answer?
Yes.
to summarize, for any f, there is indeed its own set of full measure where you have you have convergence, okay? And on set of zero measure, you may have who knows what. And now if you have a dense set of functions in L1, an inseparable case you do, dense countable set, then you happily, at least for that countable set, get unified set of full measure where you have almost everywhere. And that's a natural technique, okay? Can we go back to unique ergodicity?
No, we have one more question. That's fine.
Please.
Okay, so the question actually about the unique ergodicity. So do we need the system with this measure to be ergodic, or it will follow from the fact that the measure is unique?
Very good question, thank you. Yes, if measure, oops.
Did we pay for Zoom? This is they didn't pay.
We can hear you. There is no problem with the sound.
No,
You
there
can-
is.
Is there any other technical problem?
Yeah, we have a small one, but I don't think it matters.
Okay, I think at least I see myself.
That's not what you want?
But I think we can continue.
Yes. So can we then continue, Jakub? You see and hear us?
Yes. I'm sorry. I missed it. Did you answer the question? Or?
We'll answer it one more time. If measure is unique, then it is automatically ergodic, and that's why it's equivalent to the following. For any f in C of x, and for any little x in x, 1 over n f of t n x converges to integral of f d mu. Okay? So that's very convenient. And this is really equivalent form of unique ergodicity. It's a good exercise to show if this is always the case, then you have ergodicity, and that's the dream of any mathematician, to deal only with uniquely ergodic systems. And we will see that they, of course, they form on one hand special case, but there exists a very interesting theorem. It's called Jewett-Krieger theorem, which tells you that any measure-preserving system with a fixed measure is isomorphic in measure theoretical sense, which I don't want to start defining, to a uniquely ergodic system. So unique ergodicity on one hand is definitely not there when you have concrete examples, but if you fix a measure, then there's always a uniquely ergodic model. In any case, I'm going back to start using this new convenient concept. I'm introducing it to show how some things get suddenly nice. And so let's try to generate from, you see, the secret, convenient secret is that this is good for any point. So you can always choose a convenient point, and they will get the right limit. And maybe by choosing convenient point and convenient transformation, which is uniquely ergodic, I can recover some interesting classical results on uniform distribution. So for example, take x to be unit torus, and Tx is x plus alpha rotation. So instead of writing mod 1, I say x plus alpha on T. And suppose alpha is irrational. And it's a not so hard exercise to show that rotations on irrational rotations on unit circle are uniquely ergodic. I leave it as an exercise. It should be obvious to those who know that there is always a unique Haar measure. And because n alpha is dense, this you don't have to work too hard. You already can get it. Okay, so in any case, Haar measure, Lebesgue measure, Borel measure, for rotation, Lebesgue is just completion of Borel. But we have unique ergodicity. And so I can choose a very convenient point. So take x equal 0, then Tn of 0 is n alpha, and then you have 1 over n f of n alpha. So mod 1 is pre-assumed here because I'm in the torus, and this goes to integral of f on my space, which I again identify for convenience with 0 on the interval. And this is, of course, the same as n alpha mod 1 is ud. And this is true, by the way, for any f. Okay? Let me stress one more thing. On one hand, it's the dream of every ergodic theorist, but don't forget, you deal here with continuous functions and continuous setup. The difficulty sometimes with pointwise is because you are with abstract L1 space. Okay, so here, of course, it doesn't apply to L1 functions. It's purely continuity or Riemann integrability. And we are happy with this because we are applying it to uniform distribution. All right, so far we didn't get anything exciting, but maybe I can go back and get something a little bit more interesting. And this will be the following example. Again, it's two torus now that I'm with. And it goes under my T to transformation x plus alpha, y plus 2x plus alpha. In a moment you'll see why did they choose it in so special way, but such transformations are called skew products. On first coordinate it is a rotation, and the second coordinate it is a shift of second coordinate by some function. This is a very specific example of skew product. And this skew product, by the way, what I'm explaining now was already present in Fürstenberg thesis. He already made this observation by studying skew products, you can get interesting applications to uniform distribution. And so let us calculate orbit of 0. Just I see that after lunch people are a little bit sleepy. So first of all, I should talk louder, which I try to do. And second, let me try to engage you. So can you help me to calculate this orbit? So 0, 0 should go to alpha, alpha. That's relatively clear, right? And where does this go? Thank you. That was easy. And 4 alpha, good. And then it will go to, say, 3 alpha, and then what? 7?
Kiev says 9.
Kiev says 9, Kiev knows. So 9 alpha. And so on, so we will get the t to the n of 0, 0 is actually n alpha and square alpha. Oh. You see this n square alpha, and that's what we are interested in. So I will take now function, remember I can choose any point. So for my system, I will take point 0, 0, take its orbit. I can take, if you want, I can take only function depending on second coordinate. But we already got more, by the way. Because if you properly interpret what we got uniform distribution, which I didn't define here. Uniform distribution, but it's similar definition. Uniform distribution in 2 torus of pairs n alpha, comma, n square alpha, which is neat. But just if you take only function depending on second coordinate, so if you take f of x, y, which is just g of y, and indeed you take g of 0, right? So then the orbit, then 1 over n at y equals 0, 1 over n g of n square alpha will go to integral of g. So it should be integral on 2-dimensional torus, but it depends only on second coordinate, so it, in the end, will be just this. And as you see, we got a good thing if you didn't ask, if you believe that this is a uniquely ergodic system. This is uniquely ergodic system, and hence we very conveniently recovered the result of Weyl, and why it is uniquely ergodic. First of all, we already sort of agreed that this is uniquely ergodic. And then there is a general lemma due to Fürstenberg that for such extensions, for extensions of your system, the extension has to be ergodic, and if what you extend was uniquely ergodic, then the result will be uniquely ergodic. So there is general fact which promises unique ergodicity. You may want to try to do it, by the way, directly, by using maybe Fourier analysis, and there is a danger that it will be circular argument, because maybe at some stage you will have to use the fact that n square alpha is uniformly distributed. So let's at least accept that this is uniquely ergodic. Hence you have this result, and you can start getting ideas that maybe it's only beginning. Why not to get n cube? Let's get n cube and I will move on, because time is running faster than I thought. But we had misconnections, right? So,
Horrible misconnection.
which means some extra time. In any case, let me erase here for now. And how about this system? X, Y, Z, that's again, this time in 3 torus. And it goes to x plus alpha, y plus 2x plus alpha, z plus 3x plus 3y plus alpha. Now I hope you are already not sleepy, so I don't ask you to start helping me to calculate it, because I want to save time. So you will take my word that for this specific system, t n of 0, 0, 0 will be n alpha, n square alpha, n cube alpha. Not bad. So again, you feel that this is something too special, but then you can show that by playing just this game, you can get any polynomial. By the way, here also polynomials are already lurking, because if I take projection to one of the coordinates, I can get already some polynomial expressions. But in general, and this is fact which you can find in particular Fürstenberg's book, he does it a little bit differently because it's not super unique, but idea is totally unique. What is the idea? To generate, and this I have to explain maybe because it's very important ideologically. I know only two possible approaches to uniform distribution of, say, n square alpha. One approach is due to Weyl, and this is relying in more abstractized idea, which is called differencing technique. It relies on the fact that derivative of n square is linear. Let me not say more, but there is so-called van der Korput trick, which does exactly that. And so that's about differencing or differentiation. And when you will analyze what we did here when we got 4 alpha, 9 alpha, and all that, you will see that behind this is actually integration, so to say. Because it's a sum of the sequence 1 plus 3 plus 5 plus 2n minus 1. It will be a perfect square. So there are only two approaches that I know. If you know of any additional approach to prove uniform distribution of n square alpha, tell me. Unlike multiple proofs of denseness of n square alpha, I know a few. To prove uniform distribution of n square alpha, as I say, there are, to me, known only two approaches, Weyl and Fürstenberg. All right. Let us move now to number theory. Well, it was already a sort of number theory, but let's move to prime number theory. So I want to erase something. I think by now you all remember the definition of uniform distribution, so I will erase this blackboard. Any questions before I erase? Jakob, can I erase left blackboard?
Yes, I think so.
Okay. So, so Terry already mentioned definitions of these functions. This is so-called big omega. And this is number of prime factors of n counting multiplicities. So omega of 1 is 0, omega of 2 is 1, omega of 12 is 3. We agree. Okay? On every prime it's value 1, but if it's a product of primes, you count them as multiplicities. It has a, by the way, let's remark that this is absolutely additive function. Omega of and m equals omega of n, omega of m for any n. It has
Plus.
what? Plus. Yes, plus. Thank you. You see, it was not enough space, so I decided to squeeze it. Omega of n plus omega of n. And now there is a, this is absolutely additive, and there is just additive brother of this, or sister, I don't know, it's little o. It's the same thing, but we count only up to here. We don't count multiplicities, okay? And so for little omega, it is a little bit different count, but surprisingly these two functions, and we will not deal with this in my talk, I just make a fast remark, surprisingly on average, these two functions behave practically the same. All right, much more important function. So maybe, since I don't think I will use it, but for now, much more important function is Weyl, which is just the same as omega of n, but multiplicatively so. So this is something which Terry already mentioned in his talk. Enormously important function. In a moment, we'll see why these things are so important. So, let's consider the following two sets. S1 is all n such that omega of n is even, and S2 are all n for which omega of n is odd. So this is a finite partition in two sets of all the integers, either Omega would be even, or omega would be odd. And if there is any independence between additive and multiplicative structures, we started talking about this already today, maybe you want to guess what is density of each of them. Is there any way to prefer one over the other? So we have consensus that density of S1 equals density of S2 equals 1/2. Okay? It is our mutual guess, okay? Now what is so interesting that this mutual guess is equivalent to PNT, which with the Weyl function I could formulate this way: 1 over n lambda of n goes to 0. You remember it was discussion which we don't touch about speed of this convergence. If it is fast enough, you get to the level not of PNT but to the level of Riemann hypothesis. We don't go in this direction now. But now, for my curiosity, when I said that this is our mutual guess, was it totally agreeable that these two sets should have measure density 1/2? I don't know. Today, people are much more quiet than usual. That's not only lecturers are tired. Okay, so in any case, this is a fundamental fact of interest that there is some potentially uniform distribution of omega in residue classes. This is actually a theorem. So let me formulate it as such. Maybe I need more space here. Well, but maybe I still, since I wanted to keep everything compact, so this is one version of PNT. This is practically the same version of PNT here. And how about this version of PNT? But I have to introduce Möbius function. So this is yet another important function. So it is 0 if n is not square free. And it is -1 to power k if n is square free and is product of k primes. Okay, so Möbius function is especially important. So naively I would say that Weyl function and Möbius function are the most central functions in those aspects which we want to talk about. This one is especially useful because it plays a role in all kinds of inversion formulas in number theory, but in any case, you have a feeling that it should be random maybe, because as you go along square free numbers, how can you guess, will it be even or odd number of prime factors? And this function will be switching from 1 to -1 depending on that. So it turns out that this is very, very random function if you disregard the fact that on square free numbers, on square full number, no, on square on not square free numbers, it's 0, and this is +% of all numbers. But otherwise, it's very random. And there exists nice additional form of PNT. Goes to 0. And this is the same as saying that lambda of n goes to 0 when n is square free. And then it's, of course, between n and 1. And that's yet another form of PNT, and maybe that's good enough for us. So this is, again, PNT. Okay. And now I'm going to state a theorem. And from now on, for some while, the material which I will be delivering is from joint work with Florian Richter. And so here's the theorem. let x be mu, let x mu t be a uniquely ergodic system, then for any f in C of x, for any little x in x, 1 over n f of t to power omega of n x goes to integral of f d mu. So any questions about the formulation? You see what I'm doing? It's speaking again about the interaction of additive and multiplicative structures. I'm using additive averaging, but I'm going along arithmetic function which deals with multiplicative properties of numbers. It's sort of surprising that this is true. And it is true. That's our theory. And what I want, yes, please.
Is the ergodic version true?
Say it again?
Is the ergodic version true? If you just have
Which
an
equation?
ergodic, if you just have an ergodic system, is the
Excellent question. A little bit premature because we're still with continuous setup. Since you asked, so let me repeat Ashwin's question. People, we remember what is capital omega. And we remember what is lambda. And we remember what is mu. Then I will erase. So question is, Ashwin's question. Ashwin, if you want to make a conjecture, we'll call it conjecture.
conjecture it's true.
Okay, so Ashwin's wrong conjecture. For any f in L1, 1 over n, f of t omega of n, x goes almost everywhere to integral of. No, unfortunately, it's good try. Unfortunately, it's totally wrong, and there is a paper by Caitlin Lloyd, maybe a year ago. She shows that actually it's as bad as it goes. You can find L infinity function so that lim sup will be, suppose between 0 and 1, lim sup will be 1 and lim inf will be 0. This is a phenomenon of interest, especially for ergodic theorists. When things don't work, they extremely don't work. This is the case. And I have interesting other examples of number theoretical nature, but I'm afraid. Okay. So if time will permit, I will mention similar phenomena. So this is indeed.
You're negotiating with the wrong person.
Yes, exactly. The chair is Jim.
Hello. How do we do today? Okay, so it's continuous business. We're already lucky that we have it for any. It's still too lucky to have it, you'll see in a moment, because it gives you huge applications just from continuity situation. So I will erase it here. And
Question?
yeah, please.
How about little omega?
How about?
Little omega.
Same story. Same for little omega. I just don't have immediately super fancy applications. True for little omega, and then again, anticipating potential question, I can tell you that one should ask, and we have some interesting answers for which arithmetic functions you have similar result. So what I told you, this is theorem A in our paper. Go and check theorem B. It will be about class of arithmetic functions for which it's true. But in any case, I want to start applying this result. And so take x to be 0, 1, just 2 points, we should agree that it will be some super trivial application, right? It's the most primitive case I can think of. A space made of 2 points, and transformation x going to x plus 1 mod 2. And then if you take, I don't know, f of 0 to be 1, and f of 1 to be 0, and you create this, for this f, you calculate it, it should go to integral of f on my space, and you do a little bit, very little bit of checking, but you already see that I will get one of those equivalent forms of PNT with omega. And so this means that it implies PNT. That's good news. So our theorem is giving PNT as a special case, as a very special case. Let's see what else I can milk from our nice theorem. And how about taking x equal 0, 1, m minus 1 for some m, and tx is x plus 1 mod m, and then you do some checking, and then it leads to the following fact. The sets, let's call them SR, all n for which omega of n equals r mod m, all have density 1 over m. This is a generalization of the result about even and odd spread of omega of n. It's non-trivial, at least classically. This is theorem due to Selberg, 1939, and independently Pillai, 1940. It's classical, non-trivial result. For us, I leave it as an exercise to do some similar thing. You take characteristic function of singleton R, do calculations, you get that. How about then yet another example? X equals t, and tx is x plus alpha, alpha irrational. And then you get the fact that omega of n times alpha is uniformly distributed, or let me put it, mod 1 is uniformly distributed. And that's another famous theorem. Maybe I should explain why this follows. You take this transformation and you apply it to exponents, e to power 2 pi I n x. When you put it in, it's more or less clear that you will get, at least for these specific functions, correct limits. And by Weyl criterion, this is the same as uniform distribution. And so this is Erdős. I think he made a remark, and Delange proved it in 1950 something. Not sure. Have it. Delange, 1950 something, okay? And interestingly enough, Erdős, when made the comment, he said it's not so trivial. And then when Delange proved it and you try to read it, you agree that it's not so trivial because his proof is lengthy and technical. And let me then explain one thing just to be fair. What we get what we want. We want to get uniform distribution. We get uniform distribution. People on the other side, they want estimates. And to get estimates is much harder. And sometimes only through estimates you can get the proof. That's actually the case when it comes to uniform distribution along primes and all that. So because of the traditional classic method that they use, you have hard proof. But if all you want is just qualitative fact, this theorem does it easily. Okay? So far, we see that already for relatively primitive examples, you get already something classical. Now, you remember through Fürstenberg systems, those Q products, we had a way to Weyl theorem on uniform distribution, which I never formulated, but I hope it's clear what it is. So, using unique ergodicity of skew products, one gets the following result. If G of n is a polynomial such that one of Ci is irrational. When I say one, I mean at least one. Then G of omega of n times alpha mod 1 is UD. Whatever I already calculated together with you would show to you that this is true for n squared times alpha, or omega of n squared times alpha, or omega of n cubed times alpha. And you take my word that by Fürstenberg method you can create dynamically any polynomial. And then apply the fact that dynamically you have uniquely ergodic system producing one of coordinates to be a polynomial and use it.
What is alpha? Alpha, it should be there.
Here, there should be no alpha.
Alpha is here.
No, but G is already.
Ah!
I think you
No,
want to
thank
get
you,
rid of it.
thank you, thank you. So, yes, alpha didn't have to be there. Okay? That's, of course, not the end. We only scratch the surface. There are so many non-trivial uniquely ergodic systems. The problem is, that is often the case, how to calculate. Here we had very convenient dynamical systems that you can calculate explicitly the orbit. You would know what is t to the n of a specific point. Any other system where you can do it, and we have examples in our paper. There are other examples. One of the most interesting is, so I will say only briefly.
Okay, we've come to the classical end of the talk, but we now proceed.
So it will be normally another 15 minutes. No. Oh,
No, this is the classical end.
and now we go to.
To the sort of the.
I felt that something is wrong. So, okay, now we are in the, how do they call it? Neoclassical.
Overtime. No, yeah.
Neoclassical part of it.
Neoclassical, yes.
So I will say a few words, first of all, about other interesting dynamical systems. So these are translations on manifolds of this form. This is a specific case. This is so-called nil manifold. You take real numbers, matrix 3 by 3 of this form. They sometimes call Heisenberg matrices. And then you take n, m, l, and you take a factor space. And it is a compact homogeneous space. And as in every homogeneous space, you can do transformation cosets to cosets. And then it turns out that here you can do some calculations, and you get plenty of those generalized polynomials, those which have brackets. So there is new, and by the way, here I would say that to get this kind of result, maybe traditional methods of number theory still maybe can do. But with those bracketed things that we can also get as a free outcome, I think only dynamics was for there. So now, since time is running out, or maybe ran out already, I want to formulate one more corollary of this because it's a good bridge potentially to Mariusz and Joanna's talks and for my also open problem business tomorrow. So I have to formulate that. And okay. So I will erase here. And we'll formulate some some more results from that paper. So one of them I think is of interest. You take n is square free, and you take f of t omega o n. The setup is as always, uniquely ergodic t, for any continuous f, for any x, something happens. And this goes, can you try to guess what is the limit? I don't have too much time, so guess fast. What would be the limit there?
Integral times the density of those 6 over 5 square roots.
Very good. You knew it before? So in any case, that's correct. This is the result. And why it is so interesting? Because if I rewrite it this way, 1 sub square free times f of t omega o n. This goes to integral of 1 sub square free times the integral of f. Let's look at it. So this is an instance of independence. You see, I wrote this integral, it's agreeable, so density in discrete situation is analog of integration. So this is the size of my set, product of sizes, and this is product of sequences. And it doesn't take too much imagination to think of this as a sort of a generalized scalar product, and this is independence. If integral of f would be 0, then it would be orthogonality, they will go to 0. But I really like the idea of independence, okay? So this sequence and this sequence are independent. This is, let me just write one more result, which is another corollary of what we have, and then we'll be, so, well, goes to integral of f is alpha is in z, and 0 if alpha is not in z. And this, by the way, for some of you who are in the know, this is a qualitative, not quantitative, so qualitative version of classical Davenport result. That again can be viewed as orthogonality of this with this expression. So either independence or orthogonality, these are sides, and tomorrow it will be easier to keep talking about this. These are at least very related to Sarnak's conjecture. So I will just formulate it in very easy terms. And so Sarnak conjecture, don't be deceived by this expression. This is S. I will write another. Let me write phi times, say, lambda over L. And it should go to 0. I could write Möbius function here. It depends. It doesn't matter, right? But that's another orthogonality. That's Sarnak conjecture. I say that's Sarnak conjecture. I should tell you what is meant here. S is a homeomorphism which has 0 entropy. Entropy was not defined yet, maybe tomorrow it will be, but having 0 entropy means it's as deterministic as it goes from point of view of dynamicist. So if this is very deterministic, and this, as we started agreeing, is very random, they should be orthogonal. I claim... Sorry?
Conjecture or theorem?
This is conjecture if S is general and 0 entropy homeomorphism. That's Sarnak's conjecture. S has 0 is a homeomorphism and it has 0 topological entropy, and let me not start defining it. Good luck, Mariusz, with you tomorrow, and Joanna. But if this is of very low complexity, and that's what I want to stress, determinism and low complexity are very close in some ideology. Very low complexity, very high randomness should be orthogonal. I suggest that you think about...
What is phi?
Sorry?
What is phi?
Some function, continuous function. I just didn't want you to think of this expression the same way as you think about this expression. But, so, phi is in C of x. So, idea is that it may be, and I will try to make the case, that what we have in this theorem, and rather in its corollaries of this or that kind, is some special cases of Sarnak conjecture. It's something about independence. But what is really lurking here behind, and that seems not to be present here, here we have two actions. So let me say this, and this will be. This comes from, as you remember, from x going to x plus alpha mod 1. This is, as nice as it goes, action of z, z plus. Now, if you think about this action, so t was additive thing, but when I write t to power omega of n times m, this will be t omega of n times t omega of m. Oops, this is not additive action, it's multiplicative action. It started with additive action of powers of t, but because omega is an additive function, this is now, in operators, multiplicative action. It's action of n times. I hope that's totally clear here, right? So we have now two actions. One is multiplicative, one is additive, and they are orthogonal in this sense, or independent. That's our new take on Sarnak conjecture, which I will try to push forward tomorrow, at my tomorrow talk. But what is lurking behind this whole business is new way of thinking about independence of additive and multiplicative action, and we talked about this, right? It's very, very challenging and interesting direction of thinking. And that's all for today. Thank you so much.
Okay, any questions for Vitaly?
Yes, please.
So in the end, you said you have multiplicative action of natural numbers by t, but in this action, all primes act the same way. So can you imagine some version of this result where primes act by different operators, which may be commute?
Yes, very good question. So I didn't have time. I would develop. So in any case, it's a very good question, and the point is that the next question would be indeed that's very specific multiplicative action. So to say one parameter generated, we know to say more, but that's where open problems start. And we don't have any definitive result. So we have sufficient result for something of this kind. But for what I really am interested in this orthogonality, we have only heuristic principle and conjecture. And I will try maybe to mention it too.
Keith, any questions?
Not for the moment.
Any more questions in Warsaw?
Yes. So I have a question related to this uniquely ergodic system. So is it possible to replace power n with integer part of n times t? T is a parameter between 0 and 1.
So instead of this expression,
yes, integer
write
part
1 over n f of t, integer part
n times t small and or a, say, letter
alpha.
a.
Alpha? A.
And a is a parameter between 0 and 1.
A or alpha?
A is a variable as well.
Yes.
A is a fixed parameter.
Fixed parameter.
It's an alpha.
A is alpha.
So if A is varying, then maybe you want to average over this A as well. But
Okay,
if A is
first
fixed,
of all, pointwise convergence if A is fixed. Is it true?
I don't know. That's the beginning of interesting question. So if you have uniquely ergodic system, not translation on the torus where I know many things, including positive answer to this. But if it is general uniquely ergodic system and you take here generalized polynomial in the sense that you see, you start with this, but why not this, right? There are many things of this.
I started with this for a very particular reason, which I can explain later.
Okay, so let me just give you the answer, the situation that I have a positive answer, but it's not general situation. If this T is a translation on nil manifold, I know to answer it, at least to explain what's going on. If T is general, uniquely ergodic system, I don't know.
And if you stay on a torus, is there uniformity in this parameter for convergence?
Oh, if you're on the torus, if T is rotation on the torus, then you will get even this kind of limit. Which, by the way, somebody asked, Ashwin asked about pointwise convergence. You could ask also whether you can replace where it should be here. How about doing 1 over n minus m, summation from m to n? That's also natural enough question, which is behind the notion of Weyl distribution. And that's behind the ergodic theorem of von Neumann, which is convergence in norm rather than pointwise. This is also wrong in this setup. But on torus, since we come from uniquely ergodic systems and they can see it as a manifestation of ergodic theorem, then it will be good with this. So this can be done with uniform averages.
And this means that you can replace even with a random walk this power.
If you like to walk randomly.
And this gives you very close to your theorem because of this, what I told in my talk, because this omega n is approximated by sum of independent variables. So by a random walk.
There is a connection. So very soon, if you'll keep talking, they will be bored, but we will get to Erdős-Katz type central limit theorem. So there are connections.
Other questions?
Yes, here is a. Oh, but ask Kiev first.
Kiev?
Any questions in Kiev? Well, yes, there is a question.
Hello, sir.
Hello.
Unfortunately, I didn't understand too much, but I have a question on the topic about topology and everything related. The problem of complexity. For example, if we take a big task and need to enumerate a lot of variants to check some solution. And if complexity grows very intensively, if we look onto such a task from different dimension, how should it influence onto number of such enumerations, or whether can we create some other equation which would be much simpler than from initial dimensions?
Well, I'm not sure I can answer this. It's a little bit too non-mathematical for me. Here we don't deal with dimensions. We deal with abstract situations. In general, complexity, I didn't define it either. But complexity should be thought of as something algorithmic. For example, number of words, or if you have alphabet on given number of symbols, number of words of length n would be indication of complexity. If it grows exponentially, it's very complex. If it goes polynomially, it's maybe low complexity. That's the way we think about those things. What you describe something comes from different angle, and here I just cannot make any good comments. Sorry.
Thanks. Just some addition. On my suggestion, by switching between some dimensions, the equations should also change, and there are a lot of samples, for example, from theory of relativity. When speed increases, the picture of molecular structure also change too much. And just a second. That's why it should be some function to convert one algorithm in one dimension to some other algorithm in other dimensions. And on analogy like transformation of Laplace or something like this. So thank you for your comments. Thank you very much.
Yeah, and sorry I could not say more. Thank you.
Other questions?
So maybe just a quick question. So the examples of uniquely ergodic systems you mentioned, they were all of algebraic origin. And essentially you had these Q extensions. Do we have any examples which do not come from these algebras?
Yes, that's a good question. Thank you. There is a possibility to construct, you take this space, this is your X.
Sure.
And you take just fix any sequence, X sub n in X. And you take the transformation would be X sub n goes to X sub n plus 1. It's a shift. And now you can even formulate what is the condition for unique ergodicity. This is 0 on sequence, so you can make pretty precise statement what the unique ergodicity in this case will mean. It means that the words of any fixed length have correct frequencies. And then you have non-trivial combinatorial task if you want to create something novel, interesting. The immediate question which was open and was solved by Easy Katznelson, I think in 70s. Can you create uniquely ergodic system of positive entropy? Because pay attention, we didn't define entropy, sorry, but entropy is low complexity. Sorry, I didn't define complexity, but systems which we considered, rotations, these isometries, any isometry has 0 entropy. Then the second example was skew products. These are so-called distal systems. It's theorem of Bill-Perry that any distal system has 0 entropy. So the examples of 0 entropy. Can it be a positive entropy? Yes. So Easy Katznelson gave a construction, and since then there were other constructions of a sequence, on 0 on sequence, whose orbital closure, I forgot to explain what is the system. You take an infinite sequence, the transformation is clear, and then you take orbital closure of the system. It doesn't have to be the whole space. Suppose your sequence is 0, 1, 0, 1, 0, 1. The orbital closure will be 2 point set. It still will have 0 entropy, but the end will be, and in this case will be uniquely ergodic. So you can really get, and that's interesting and a priori not obvious, but you can get systems of positive entropy, which are still uniquely ergodic. So unique ergodicity and entropy are not correlated. But there is a trend in mathematics that very low complexity forces unique ergodicity, but that's a separate topic. As I say, if you want to apply nicely whatever I described, it would be nice to have so concrete example that you can calculate numerically, so to say, orbit of a preferred point. Then it will give you new orthogonality example in very concrete terms. And that's interesting.
Okay. So let's thank Vitaly for a very beautiful lecture.